Hello again, it's Michael Houtis here, and this is the second video that I'm making, and this time we're going to look at how you can use SDT Assistant to fit an ROC curve, and we're going to keep it simple by ensuring that the ROC curve that we fit won't even require any data entry. We'll just use the default data that comes in the software when you start it up. So to begin, we just open up the folder where we have loaded SDT Assistant, and then we can just run SDT Assistant, and here we go. Now, as promised, it comes with data, and so we have S2, or what might be called in the literature signal, and S1, which might be called noise. And I prefer to go with just numbering the stimuli because it gets rid of the connotations that signal and noise might have, which seems to trip up some students when they start looking at this. So what do we have here? We're opening up on the software, and we can see immediately that it opens to an area where you can fit ROC curves. So what do we have here? Well, we have 6 numbers here from 1 to 6, and these represent the 6 rating categories that we have for these data. Now that can be changed to other numbers simply by clicking on this here. So now we're down to 5, 4, 3, or we can go higher. So multiple options. The most that you can go to that will fit on the screen is 10 rating categories, which you probably would not want to go beyond that really, but you can by importing a file of data instead of entering the data on the screen. But that's not something we're going to talk about today. And in here we can see we've got the frequencies already entered for each of the rating categories and each of the 2 types of stimulus. So this is our contingency table, and some things you can do here. It opens up with this data. If you don't want it, if you click on C, it will actually clear that line of data. So there we go, we're starting from scratch at this point. We can choose whichever number of categories we want. Let's say we have 4, and we can just go and enter our data into these cells. Now I don't actually want to do that, and so I'm going to restart this program and bring those data back. And so we can restart. Here we go, data come up again. And so we have all we need here really. The other thing that I'll show you why it's here soon is we've got this button that says flip. And when you click on flip, it actually flips the data within each row across columns. So column 6 becomes column 1, 5 becomes 2, etc., etc. And the reason for this is that some people find it difficult to figure out which way around their frequencies are supposed to go. And this is a quick way of testing whether you got it the right way, or rather if you have it the wrong way, to change it to being the right way around. So what else do we have here? Well, the final thing we need to do before doing an analysis is to select the model that we want to fit to the data. So currently this is set to the unequal variance model for yes-no data. So data that are collected from a yes-no task, and in this case a yes-no task with ratings. Another name for a yes-no task is the A-not-A task. So this applies to the A-not-A task with ratings. And if we click on that arrow, we can see there are a number of different models here. And so the one we're on is the unequal variance model, but then the other one that's fairly common is the equal variance model for yes-no data. So this assumes that there are equal variances in the perceptions for the 2 types of stimuli. So let's use that one for now. Okay, we've selected it. Now what we want to do is actually, well, do the analysis. And that's relatively straightforward. You click on Process and Process Current Grid. And there we go. We've done our analysis. This is a quick and dirty version of the ROC curve. It's by no means meant to be publication quality, but it just gives you an idea of what your data say and the model that has been fitted to it, and you can eyeball it quite nicely. Okay, so we've got 1, 2, 3, 4, 5 data points. You always have one data point less than a number of rating categories, which we had 6 there. And we have the curve, the best fitting equal variance curve. We can sort of tell it's an equal variance curve because it's symmetrical, and it's symmetrical about the negative diagonal, which would be the line that runs through this way. Okay, so let's talk about the flip button again. What if we flip the data? Okay, now they've been flipped and we process this again. We find we get this very strange looking ROC curve. Okay, as soon as you see a strange looking ROC curve like this, the first thing that should come to mind is that you've actually entered your data in reverse order from what they should be. And so if that happens, you flip and you will get the correct fit over here. Now there are of course certain circumstances where you're looking at relative differences between large amounts of stimuli or many different stimuli, where you may actually get negative ROC curves, or curves that bow downwards instead of upwards. This is possible. It's unlikely unless you've got that specific use case. And so this is a way to quickly check that you've entered your data in the correct manner. Okay, so if we move this over a little, we can also now look that there's a whole bunch of stuff down the bottom here that is quite important. And so if we go to the top of this list, we can see that our data has been processed in various different ways. Here's the original data that we had, and it tells us we had 597 S2 trials and 591 S1 trials, and that looks exactly like this. And then we've got the original proportions matrix, which converts all of these numbers into hit rates and false alarm rates. And so we get these two rows. And then we have the processed data matrix, which in most cases will look identical to this matrix up here. But there are some situations where you may need to apply some corrections to your data that will show up in this particular section here. And the software can make alterations all by itself, but you will see what has been done by looking at this processed data matrix. And then the processed data matrix gets turned into a proportions matrix. Okay, so in this case, these two sets of numbers and those two sets of numbers are equal. Now, the other thing we might be able to say here is that these are false alarm rates and hit rates, as I just mentioned. So 0.014.29 is actually this data point here. And 0.083, 0.548 is that data point there. So the data points are simply these pairs plotted on the ROC curve. Then we've got a whole bunch of things down here that initially we don't really need to be concerned about. One thing that might be worth looking at initially is this value here. What you're looking for is a number that's very small, like 1.09 by 10 to the negative 13 is quite small. Okay, so this is telling you that the derivatives of the fit are pretty much right where you would expect them to be, very close to 0. So you have a decent fit. Then we've got things like variance-covariance matrices, which we usually don't need to access directly, but they are there if you find a use case. And then we have things that are more important. So we've got d prime of 1.298 here. Now this is an initial value, so that's just obtained by doing least squares regression. And it's called an initial value because it's a starting point for the maximum likelihood fits that follow. Here are the final values, which is the maximum likelihood fit for D prime, and we have the variance for D prime and the standard error for D prime. So we can look at whether D prime is different from 0, or if two values of D prime obtained in this way are significantly different from each other. And then we have the criteria, because this model doesn't just have one parameter, being D prime. It has several. It has criteria representing each of these points. And so the criteria are actually fitted values as well. And we have, not surprisingly, got 5 of those. You may have no use for those, or you may have a use for those. If you are particularly interested in bias changes or response bias changes in participants across conditions, this is how you would look at that. And I will point out at this point that here is the measure C, which currently I think is probably the best criterion measure that we have, although the jury may still be out a little on that one. And then down here we've got area measures. So we've got P brackets A, which in sensory evaluation is called the R index. It's also called A subscript G in Detection Theory Use Guide and several other publications. And it is the area under the ROC curve obtained by fitting straight lines between the points. So rather than a nice smooth curve like this one here, we start at 0, 0, we have a straight line to there, straight line to there, etc., 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 and final line up to there. And this area is the area under that ROC. AUC for area under curve, in this particular case would be equivalent to A subscript Z, is 0.812, and it is the area under the smoothed curve, or the best fitting ROC curve. Both of these are good measures of sensitivity, and some people might think that something like the R index here, where you're just putting straight lines into your ROCs, is, well, a little bit of a shortcut. And in a way it is a shortcut, but the other thing is that it actually corresponds directly to several statistically interesting facts. And the one that I'll mention is that that area there is equal to a scaled version of the Mann-Whitney U statistic. And so it has a very nice connection to non-parametric statistics. Okay, and I think the next thing we'll quickly look at is fit statistics for the curve, and this is the G-squared statistic. It's 32.97. The degrees of freedom are 4, and the probability associated with that is very, very small. Okay, now fitting models to data, you often find, especially when you have a lot of data, such as the quantity that we have here, that traditional chi-square measures are, well, highly significant. And when these values are highly significant, it means the model is not a good representation of the data. Okay, so it's a sign that our model isn't that good, but it's very hard to have a very good fit if you've got about 1,000 data points. And down here are some other useful statistics, such as the log likelihood. Best fitting log likelihood is minus 1936.73, and then we've got various information criteria down here. Now, we're not going to really talk about those anymore at this point, but in a future video I might go through and give an idea of how that might work. But what we can remember now, for now, is that G squared is 32.97. Let's just say 33. Okay, so if we go back to the top here and we change our model to be the unequal variance model, what happens to our fit? Well, that happens, our fit becomes much better, it would appear. And we can see the unequal variance model can accommodate asymmetry in the data. And so we have the curve going pretty much through all the data points. And if we look at LL again, or rather, that's not the one we wanted to look at, it's G squared, we find it's now 1.48 rather than 33. So we have a much better fit. And we do also find that the probability is 0.68, and therefore this is not a significantly different fit from the data. So we still can get a good fit with a lot of data, maybe if we're lucky. Okay, now the unequal variance model, everything is pretty much the same, except that now we have two parameters of interest, and they are traditionally called the intercept and the slope, and we have initial values and final values, and then these two parameters are normally converted into a single sensitivity measure, which is dA. It's not d prime. You cannot have d prime with unequal variance, so it's dA. And we find that dA is 1.239. Now the nice thing with dA is that if there really are equal variances, you can still calculate dA, and dA equals d prime. So they are nested within each other, these two models, unequal variance and equal variance, and dA, if variances are equal, becomes d prime. And then we've got various criteria again, and the one that we recommend is CA, which corresponds very cleanly with dA, and also simplifies down to C if variances are equal. At this point, I think that is all I'm going to talk about for this session, and I'll just have a scan through, see if there's anything else. There's nothing else in particular I think I'll mention. So the easiest thing to do is to practice with these data. Don't change them, and then you won't get anything wrong initially, and come to terms with what the results actually mean. This here is the manual that comes with SDT Assistant, and it works through all of these things, but it's fairly dense. And so the best thing to do, I think, is to actually run the software and work your way through doing specific things with it, in this case, fitting an ROC curve. Okay, on that note, I'll say thank you for listening, and I will be back again at some point with another recording. Okay, thank you very much.